Welcome to the Explainer. Today we're going to decode a really fundamental concept in data science and math, linear transformations. It's a huge question, right? But the answer, well, it actually starts with a pretty simple visual idea. So let's start there. Let's just imagine our data in a very specific way. Okay, just picture a sheet of graph paper. Every single bit of your information, every data point you have, it's got its own specific coordinate. It has its own little home right there on this grid. Now, a transformation is really just a fancy word for a function or a rule that takes each of those points and moves it somewhere else. I mean, the points could get totally scrambled, warped, shifted. You can imagine it could get pretty chaotic. But this is where the magic happens. A linear transformation, you see, is predictable. It's well-behaved. The grid can stretch out, it can shear, it can even rotate around. But the key thing is the grid lines never curve or break. And the origin, that center point, 0, 0, it always stays put. So you might be asking, what makes this movement so orderly, so well-behaved? Well, it's not an accident. This whole thing is governed by two very precise mathematical rules that define what it even means for a transformation to be linear. The first rule is called additivity. So let's think of our data points as vectors, arrows pointing from the origin to their spot on the grid. Additivity basically means it doesn't matter what order you do things in. You can add two vectors together first and then apply the transformation to the result, or you can transform each vector all by itself and then add those results together. You get the exact same answer either way. And you can really see what this means right here. Let's say our transformation is a simple rotation. So on the left, we add the vectors u and v to get that new diagonal one, and then we rotate it. On the right, we rotate u and v first on their own, and then we add the rotated versions. Look at that! For a linear transformation, both paths land you in the exact same spot. It's totally consistent. Okay, the second golden rule is homogeneity. This is pretty similar to the first one, but it's about scaling. All it says is that scaling a vector by some number, like, say, making it 3 times longer, and then transforming it, is the exact same thing as transforming the vector first and then scaling that result to be 3 times longer. Once again, the order just doesn't matter. So, okay, these are some neat geometric rules, but why are they so incredibly important in a field like data science? Well, it's because they let us manipulate gigantic data sets in a way that's totally predictable. And this quote from Soren Mitrin, it just nails the modern perspective. See, in data science, linear algebra isn't about figuring out where two planes intersect, like in your old geometry class. No, it's all about finding clever ways to describe, to compress, and to find hidden patterns in just massive amounts of data. And here's the basic workflow. It's really elegant. First, you take complex data, like all the pixels in an image, and you represent it as vectors. Second, you take that linear transformation, the rule for changing the data, and you encode it in this object called a matrix. And finally, applying the transformation is as simple as matrix multiplication. It's an incredibly powerful system. Now, because these rules are so strict, it actually gives us this powerful little shortcut. We can use them to create a simple test to quickly figure out when a transformation isn't linear. Sometimes it's way easier to prove something is false than to prove it's true. So instead of trying to prove a transformation follows both golden rules for every single possible vector, we can just look for one simple failure. And here it is, the litmus test. Remember how we said the origin of our grid has to stay put? Well, that's the key. In any, and I mean any, linear transformation, if you plug in the 0 vector, the origin, you absolutely must get the 0 vector back. If you plug in 0 and you get anything else, game over. The transformation is not linear. It's an instant disqualification, simple as that. Okay, finally, let's look at what these transformations really do to the space our data lives in. Because yeah, they can stretch it, but they can also squeeze it. And in the process, actually lose information. The kernel is such a cool concept. It's the collection of all the vectors that, after you transform them, land right on top of the origin. They get completely flattened to 0. This tells you exactly what kind of information is being totally destroyed or lost during the transformation. And the image, well, it's basically the opposite. It's the set of all possible landing spots. After you've transformed every single vector in your original grid, the space that they all now fill up, that's the image. It shows you the entire universe of possible outcomes. And this all leads to a really beautiful idea called the rank nullity theorem. Now, this isn't just some formula to memorize. It's a statement about conservation. It says that the dimension of the stuff that gets lost, the kernel, or nullity, plus the dimension of the stuff that remains, the image, or rank, has to add up perfectly to the total dimension of the space you started with. What's lost plus what remains equals the whole. It's a perfect balance. So you see, linear transformations are so much more than just math. They're the rules for rotating, scaling, and simplifying how we look at data. They give us this incredibly powerful lens to find the structure that's hiding in all that complexity. And the principles we talked about today, well, they're the foundation for how we do it.